So this is just a brief 10-minute reminder of what we've done. Chapter 1 was about the basic idea of probability as, first of all, a measure of likelihood. Probabilities close to 0 are unlikely. Probabilities close to 1 are very likely. And then you got the in-between. I also illustrated with the coin flipping that I did the first day of class and the graph that I made. The basic idea that you flip the coin more and more often. For that example, the proportion of heads, generally speaking, gets closer and closer to 0.5, the probability of heads. It's rarely ever equal to exactly 0.5, though, right? That's pretty rare. But in general, the graph was jagged. It gets closer and closer to 0.5 the more trials you have. There were more complicated ideas as well. There was the idea of a sample space, events, and then we had methods for solving problems that included tree diagrams and Venn diagrams. And those things were useful also in chapters 2 and 3. Some other technical terms included mutually exclusive events. A collection of events is mutually exclusive if when you take the intersection of any two of them, you get the empty set. There's no overlap between any two of the events. They can't occur at the same time. It's ideas with sets, intersection, complement, that kind of thing. Set notation, intersection, union. And we also had the counting principles. There's the multiplication principle, which is just a fancy way of describing the meaning of what it means to multiply two positive integers in terms of counting things, and permutations, combinations. And probably the hardest part of that was the problem solving, right? There was one example where I was unsure how to proceed at first. Very easy to get confused. So it's something to practice. I'm not going to give you extra tricky problems on the exam, but you should be able to do basic kinds of problems like came up on homework. And a couple old sample exams, you should look at the problems that we have to do, thinking about combinations, for example. That was probably the hardest part, was the problem solving. Chapter 2, we had the axioms of probability. And then also basic properties that you could prove from the axioms. We did do a few proofs. You had at least one proof on the assignment. Will I put a proof on the test? I think I have done it in the past. Examples include being able to prove, well, an axiom, you can phrase it in two ways, so I'm just double checking what the book does. The book assumes as an axiom that the probability of S equals 1. Yeah. This includes the probability of the sample space equaling 1 as an axiom, and properties includes, as one example, the probability of the empty set being 0. You assume this is true, and you should be able to prove that's true using other axioms, which include the addition rule for mutually exclusive events, and the fact that the sample space is a union of two mutually exclusive events, the sample space itself and the empty set. The intersection of the sample space with the empty set is the empty set. That means they're mutually exclusive. There was also the fact that the probability of any event plus the probability of its complement equals 1, using prime notation for the complement, something you should be able to prove. Using really axiom 3 again. think you also ended up proving if A is a subset of B, then the probability of A is less than or equal to the probability of B. That was another proof you did. You'll be able to do. After that point, we had conditional probability. By definition, the conditional probability of A given B is a ratio. It's the probability of A intersect B divided by the probability of B. That does lead also to the general multiplication rule, which we used earlier today in thinking about the M&Ms, the red and green M&Ms. We were using this generalized to thinking about three events actually for the three draws of the M&Ms. The roles of A and B here can be switched around, and sometimes that's useful to remember. Here they can be switched around as well, as long as you change what's in the bottom of the fraction. There was also independence in the multiplication rule for independent events. I called this a definition of independence. The book called this a theorem. And I called this thing a theorem. The book calls this a definition when A and B are independent. It doesn't really matter which one you label as a theorem and which one you label as a definition. They're both still true when A and B are independent. We ended up using this formula right here a lot in chapter 3, actually. You may not remember using it in chapter 3, but we did. We used it, for example, when talking about discrete random variables, we used it to, in a probability problem about baseball, right? Pretend you're, I think I used probability of success being 0.23, 230 hitter. Number of at-bats was 3. You were counting the number of hits and trying to figure out probabilities. We were using the assumption of independent trials, which led to particular discrete random variable binomial. Number of successes in n trials where the probability of success stays constant and is independent of what's happened previously. We also did negative binomials and Poisson last time and today. Of course, there were the generalities as well that you should know about, involving general PMFs, CDFs, mean, variance, moment generating functions. Guess another special random variable I was forgetting here is the geometric as well. Knowing that a discrete random variable is either going to take on just a finite number of possibilities with positive probability or a countably infinite number of possibilities like with geometric, and negative binomial take on a countably infinite number of possibilities with positive probability. And then also the special formulas for means in special cases, like the mean of the binomial is n times p. The variance is n times p times q. With a Poisson, the mean and variance are both k, like we saw today. Being able to derive those things. And then just what we briefly learned about chapter 4 today. Okay. So that summarizes the content in 10 minutes. Work on problems too.